What's up, everybody? Hope you're doing well, and welcome to this lecture in which we're going to be talking about advanced pod configuration. And what I mean by that is we're going to be talking about kind of advanced scheduling tactics using pod affinities, node selectors, that kind of stuff, as well as talking about multi-container pods and what that looks like. So here's our goals and our outline for today. So again, pod scheduling is where we're going to start off. We're going to talk about affinities and taints and tolerations, which I know some of this sounds like, what are we getting into here? Don't worry, we'll make it pretty easy. And then multi-container pods, we're going to talk about both init containers as well as some sidecar container patterns. And we'll go from there. We'll see some demos along the way. First off, let's talk about pod scheduling. So scheduling pods in Kubernetes, the default scheduler is a component that's called kubescheduler. And this component runs as part of the control plane so that when you define a pod, it's actually this kubescheduler component that looks at various aspects and figures out what node, where should this pod actually get scheduled. Now, for the most part, in the class so far, we've been focusing on just single node clusters because we've just been running on our local machines. But, clusters can span to thousands of nodes. And so the job of scheduling becomes a lot more difficult and a lot more important. And there's lots of different ways that we can schedule. Okay, let me grab the laser pointer here. There we are. So the scheduler works in a what's called a two-step operation. So the first thing that it does is it filters nodes. So it looks at the full selection of nodes and filters it down to what nodes can or should I schedule my pod onto. And then from there, it uses a scoring system to figure out the rank of nodes within that. We're not going to get too much into the scoring side of things. We're going to talk about mostly the filtering side of things. But scoring can get a little complicated, but it's also important because, depending on how you want to balance nodes or, target specific nodes a little bit more than others, that you may have different weights or different things that you want to do. Maybe you're running in the cloud and you've got different availability zones or different regions, and you want to kind of spread the workloads across those different things. So there's quite a bit that can go into it, and we're not going to get that advanced today. So we're going to focus mostly on the filtering side of things. And finally, if the kubescheduler, if it doesn't find a suitable node, well, then the pod just remains unscheduled and just says, sorry, I can't put this anywhere. Now, depending on your environment, this actually becomes pretty important. Like, for example, here at Virginia Tech in our platform clusters, we have components that are called cluster autoscalers, so that when we schedule a pod, if it can't be scheduled, maybe because there's not enough capacity on the machines that we have right now, this component can see that pod that's unscheduled and say, well, cool, let me go to an autoscaling group and spin up another machine so that there is capacity to run that pod. So there's some pretty cool stuff you can do there. Again, we're not going to get into that, but just to let you know that those capabilities are there. So the most primitive type of filtering that's available is through the pod specifications node selector field. Now this field defines labels that must exist on a node. And yes, nodes can have labels as well, and we'll see some examples of that here soon. So this example here, we have a pod that's going to be running Nginx, and it specifies a node selector that says, hey, the node that this thing is going to run on needs to have a label named network optimize and a value of yes. Okay. Now, of course, how that node gets the label or whatever is kind of outside the scope of this. But in this case, the pod is going to only be scheduled on a node that has this label. So you can think of a cluster where you may have some machines that are a little bit more network optimized than others, have fatter pipes and bandwidth. And so maybe for some reason, this one's going to receive a lot of traffic. So we want it on a node that's going to receive a lot of traffic. Other use cases might be I'm running workloads that need to run on PCI compliant machines. Okay, so maybe I put a label on those nodes that are PCI compliant, and so then I can know with certainty that my applications will only run on PCI compliant machines. So security plays a lot into this, but it doesn't have to be only for security, as is the case here. So node selectors are available, are pretty commonly used. But there are some shortcomings that come along with node selectors. So some questions of, what happens if a node's labels change? If a node was network optimized, but it's now we're changing what network optimized to mean a different set of nodes. Um, how do we respond to that? How do we indicate soft versus hard preferences? So for example, we prefer this, but it's not absolutely required, or maybe we'll put additional weight on it. And that kind of goes back to the sorting part of things after the filtering. So how can we indicate some of the sorting preferences or weights? If we want to set a preference with other pods instead of nodes, so maybe I've got a container, or I've got a pod that's the database, and I want to make sure that the app runs on the same machine as the database, so that way I'm not having to do networking to talk to it. Or I want to make sure that my pod runs in the same availability zone as another pod, so that way I don't have to pay for the network bandwidth going between availability zones in the cloud. So how can I do preferences that aren't just nodes, but maybe use the inputs for I want nodes that have other pods running on them, or pods that aren't running on it. So how can we do some of those more sophisticated things? And what if you want to use more advanced selection expressions like in? So for example, I want a label that has this key, but maybe a collection of values that it could have. Um, so with that, there's been some new work to define what are called affinities, and that's what we're going to be talking about from this point forward. And an important note is it, meaning the node selector, is not being deprecated or removed. There was some discussion in the community for a little while of now that we have affinities and whatnot, should node selectors kind of be deprecated and removed? Technically, all of the capabilities that are defined with node selectors can be defined with affinities, but it's a lot more cumbersome, and and you'll see the difference. Again, node selector was just 2 lines here, while affinities aren't just 2 lines, and we'll see some examples of that. But that also comes with more flexibility and being able to do more things. Um, so affinity versus anti-affinity, and we'll see examples of this. Affinity means I want to schedule with. So if I have an affinity to something, I have an attraction, or I want to be scheduled with um, the rules that are being defined. Anti-affinity means I don't want to be scheduled with, and so I can actually set anti-affinity rules that say I want to be scheduled away from nodes that have specific things, or away from pods that have specific attributes to them. And each of these affinity types lets us choose 2 different options. And I know these are pretty long, but they're fortunately pretty self-explanatory. So required during schedule, ignored during execution. And what that means is when the pod is being scheduled, we're going to apply these rules as part of the sorting and filtering mechanisms. The first one's required, so these things are required. Preferred means that they're not required, so it's not actually going to filter nodes out, but it plays into that second step of the sorting. So the preferred, you express a weight, and it helps specify the preference, or where those nodes or pods, or et cetera, should show up in the sorting mechanisms. Eventually, these following 2 will also be defined. And what these are, so required during scheduling, which is the same up here, but also required during execution. So what this latter part means is that eventually you'll also be able to say, all right, I want a node that has this label on it. It's required during scheduling, but later on, if that node changes values, if the label disappears and now shows up on another one, I want you to remove the pod from there and reschedule it somewhere else. So the required during execution tells the scheduler to watch for changes, and then as things change, respond to it, which might mean that pods might get rescheduled somewhere else. So those are still in the works right now, but there's a lot of kind of excitement, and there's a lot of pretty cool use cases with those. All right, so let's look at a full example. I know that there's still quite a bit here. Okay, so this example on the left here is with node affinity. So in the pod specification, I have an affinity field here, and I'm specifying a node affinity. This other example has a pod affinity, and we'll go to that. So in this case, I'm specifying at the node level the things that are required. So required during schedule, ignored during execution, and I'm going to select nodes that match this expression. And the match expressions are going against labels. So I'm going to find a label that has the key Kubernetes IO E2EAZ name. So this is an availability zone. And the value for that can be one of these two values. So again, this allows me, where the node selector was just key value, this is now letting me say, here's a key and here's multiple values that could be allowed. So in this case, this pod will only get scheduled in an availability zone, most likely in AWS, that uses AZ1 or AZ2. Now, how those nodes get the labels on them, that's a completely different discussion. I'm not going to get into that now. But again, this pod will only get scheduled on nodes that are running in either of those availability zones. Okay? The example on the right here is a pod affinity. And so now this is doing a little bit more metadata searching. Again, at the end of the day, the scheduling is going to be happening onto nodes. And so the scheduler, what it's doing is it's now looking at nodes, but also the pods that are running on the nodes to either schedule with or away from existing pods. So in this case, we're doing a pod affinity and we're required during scheduling, ignore during execution. So we're going to find all pods that have a label selector that matches this. So we're finding pods that have a security label of S1, whatever that means. Okay. And both of these examples were taken from the Kubernetes documentation. I didn't make these up myself, but so in this case, I'm going to find a pod that has a security label of S1, and I'm going to find a node that runs that has this pod, and I'm going to schedule with that. The topology key here, I won't get too much into topology. We'll talk about it in the future, but I left the field in here with the example. But topology is used for, again, if you're running large clusters that are split into different zones, allows you to kind of balance across the zones, etc. So anyways, I'm going to find a pod that has this label in it, and I'm going to schedule this this pod to run on that same node. And again, the reasons may be I want to reduce the amount of network latency that's going on, or maybe they just need to be close to each other. And so that's what affinities let us do here. All right, so let's actually do a demo here. And for this demo, I'm actually going to be leveraging, let me pull up my terminal here. I've got a Raspberry Pi cluster that I've got just running under my desk here, and it's a 3-node cluster. And so I've got Pi 0, Pi 1, Pi 2. And what I'm going to do is on each of these, I'm just going to run a watch that is going to output the pods that are running on each of those nodes. Okay, and we're going to apply this manifest here. So I'm going to deploy my little Cats demo app, Cats 2.0, and I have a node affinity that says I'm going to run this on a node that has a key of fancy node and a value of yes. Okay, again, just something I made up here, but valid use cases maybe, especially for a Raspberry Pi cluster. Maybe I want to, if I'm going to do something that's a little bit more network intensive, maybe I want to label my nodes, which ones are using SD cards, maybe, or a one that has an attached SSD, or whatever. So I can label my nodes with any kind of characteristics, and then I can use that during scheduling. So in this case, I'm going to use fancy node, yes. Okay. Now, if I try to apply this first, I haven't actually labeled any of these nodes yet. When I try to apply this, so let's describe one of these. We'll see down here, the default scheduler, it failed scheduling. And the reason is that 0-3 nodes are available. 3 nodes didn't match the affinity selector. So remember with the scheduler, it's going through that 2-phase process where it looks at all the nodes, and the first step is the filtering, and it says, hey, this pod has an affinity that requires these attributes. Well, when I evaluate all 3 nodes, that leaves me with no nodes available. I can't schedule here. Okay, so let's label my node, and let's just pick this middle one. So that's Pi 1, and I'm going to label it fancy node equals yes. Okay, and so once I do that, the kube scheduler immediately sees that and schedules the containers to run on that node. Now, if I were to remove the label, now doing this through the CLI is a little funky, I will admit. To remove a label, you put the key and then put a dash at the end of it. It's super weird. Now, if I delete the pod, let's delete this one. All right, so that pod's terminating. Again, because it's only the affinity is only required during scheduling, the other one will continue to run because it's already running. It's already scheduled. And these attributes are ignored during execution. So it's going to delete this pod. I don't know why it's taking so long. But once it's deleted, it won't be able to reschedule it. And I'll see, again, another pending one. And this will give me the same issue, saying I can't schedule this anywhere. Okay. So again, affinities allow us to oops. Let's put pi2 over here. So now pi2 has the label on it and is running the second one. So I've got them balanced across two different nodes here. And I can look at the pods. If I add wide, I can see which nodes these are running. So the first one's on pi1, the second one's on pi2. Okay. All right. Let's go ahead and just clean this up. All right. And let's jump back to the slide. So taints and tolerations work kind of in the opposite direction as affinities. So affinities I put on the pods themselves to kind of say, here's where I want to go, and it's kind of defining the attraction. Taints go the opposite way, in which I could put taints on a node and it's repelling and pushing away pods. Okay, so again, taints repel, affinity attracts, and taints go on a node to prevent pods from being scheduled. So I can put a taint on a pod or on a node to say, hey, I'm going to be doing system updates, or I'm going to be rotating this, or I need to take it out of the cluster for some reason. I could put a taint on it to say, hey, don't schedule anything else on here. Okay. And in fact, we do this quite a bit whenever we're doing updates. We will taint all of our old nodes, reschedule all the pods, and then we will bring down the nodes, bring up new nodes, and now the new nodes can be scheduled on. So they are pretty powerful. But you can also do taints. Another example that we do is we've got our main cluster and main resources, main node pool, and then we've got another group of nodes that are spot instances. So in AWS, we can have spot instances that are, without getting too much, they're cheaper nodes, but you're not guaranteed to have them forever. And so they could disappear. And normally you only get about 2-minute heads up of, hey, this node's going to go away. AWS needs it back. But because of that, again, they're super cheap. So for the most part, we don't want to run our main workloads on the spot instances. We only want to run those on our main node pool, where we know the machines are going to stay there. So for these spot instances, we can use them for like workshops or demos or build pipelines, etc. Whereas if a build pipeline fails, we can just rerun the job. Not a big deal. And so we use these spot instances to run these more ephemeral workloads that can come and go. But to prevent our real workloads, our real applications from running on them, we put a taint on the spot instances so that things don't accidentally get scheduled there. And then the way that pods can get scheduled there are what are called tolerations. So we put a toleration on the pod that says, yeah, I recognize there are taints, but I'm going to kind of ignore that taint. I'm going to tolerate that taint here, and this workload can run on a tainted node. And so, yeah, that means that in this case, our spot instances, the node can go away, but this pod is accepting that fact. And it's saying, yeah, I'm going to go ahead and work with this. Now, what that means is that the taint simply says I'm allowed to go over there, but that doesn't do the required. So if I want to make sure that my applications always run on a spot instance, then I also need to put an affinity on it as well. Okay. So here's an example here where I'm going to do I'm going to taint a node. In this case, kind of building on the example that we just did, I'm going to taint node 0, and I'm going to put a label of node type spot on it, and then this is called the execution or the flag, the effect, sorry, of no schedule. So I'm going to basically taint this node and say I can't schedule anything unless it has a toleration for this specific thing. So this pod now indicates a toleration that says here's the key, here's the value, and I'm going to allow myself to be scheduled on there. And this pod would be allowed to be scheduled. So let's give that a shot now. And let's go to my terminal. And if I look at my YAML here, we're going to see a similar thing where I have a toleration of node type spot. Okay, and right now I have it commented out. And let's, okay. I'm going to taint I1, yeah, with node type equals spot, no schedule. In fact, let's do it. Oops. And node 2. Let's even do it. Let's just do it to all my nodes. Yeah. Okay, so now if I apply the tolerations, okay, because I had the tolerations commented out, if I look at my pods, we'll see that they're not actually getting scheduled anywhere. And that's again because, well, all of my nodes going through the filtering, all the nodes have a no schedule taint on them, so I can't schedule anything new on them. So I have to explicitly say, yeah, I know you have a no schedule thing. I'm going to tolerate, I'm going to allow this application to work. So let's go ahead and comment these out. And now we see my application starting to be scheduled. So I've got 2 instances running here, 3 running over here, and then the 6th one will show up here. Now this first one probably isn't getting one because this is the master node, and so it has additional ranking that goes into that because it's the manager of the cluster. So this isn't surprising that it's splitting the workloads between those 3. Okay. So again, we can use taints and tolerations to kind of isolate different parts of our clusters or our environments and say, in order to get into this group, you have to explicitly say you want to be in that group. All right, back to slides. Now we're going to shift gears a little bit, and we're going to talk about multi-container pods, right? And multi-container pods are kind of, it's going to be a new concept to each and every one of you probably anyways. Because for the most part, we've only been leveraging single container pods, right? And the single container pods are, I would say for the most part, the standard use case. There's not many people that do much more than that, but you still can. Now, multi-container pods are special in the sense that there's a lot of guarantees that come along with them. Okay, so I can do, when I run multi-container pods, I know that all those containers are going to be scheduled together. So remember, pods are the most basic schedulable unit. Okay, so when a node is going to run a pod, it's going to run everything that's contained in that pod specifications, all the containers and volumes and init containers, all that stuff. So they're all going to guaranteed to be scheduled on the same node. In addition, all the containers will share the same network and IPC namespace. Now, I fully recognize you may not know what that means, but the third bullet point here is why that matters. Okay, it means that they can communicate over localhost. They share the same, by sharing the same network namespace, localhost to one container in the pod is the same localhost in another container in the pod. What that also means is that you have to coordinate ports. So if I'm running multiple containers in the same pod, no 2 containers can listen to the same port. So you just have to kind of be careful with that a little bit. There are different types of multi-container pods, and we'll talk about these specifically in just a minute. But at a high level, here's what they are. So init containers are containers that run before the main application. Okay, and each of those containers, if I've got multiple init containers, they will run in order, and each of them have to exit successfully before the next thing runs, whether that's another init container or the main app. And we'll see a diagram of that here in just a second. Sidecar containers run alongside the main app, so think of it as they're running concurrently, and you can do some pretty neat stuff with that, which we'll talk about as well. And ephemeral containers are a new concept that are coming along. They're still in alpha stage right now, and but I'm actually super excited for them because they open up a lot of neat possibilities when it comes to troubleshooting debugging. But basically what it is I've already got a pod running. Now launch a new container within that pod that shares the same namespaces, but since it's a new container, I can add tooling to it. So maybe I need some network debugging tools or that kind of stuff that aren't part of the main app. I can use this ephemeral container to bring in debug tools on the fly. And then when I'm done, I just exit out and let the ephemeral container go away and it's gone. So ephemeral containers are pretty cool, but they're still in alpha, so most people can't use them yet. Um, anyways, all right, so init containers. The diagram here is kind of a timeline. So they're, init containers, you start them sequentially, and they have to exit before the next thing runs. And in this case, I've just got 2 init containers. You can have as many as you want. Init containers are useful to load or register configuration. So a lot of times you'll see this as before my app, or when my app starts, it's going to load configuration from a file. Okay. And we talked about earlier of using config maps or secrets to kind of populate volumes for our containers. But that only works if you can use config maps or secrets. There's a lot of environments that may load configuration from lots of different services. So for example, here on campus, in a lot of our IT groups, we use a tool called HashiCorp Vault, which is a secret store to store our secrets. And so we can have an init container that goes and talks to Vault, grab the credentials, grab the secrets, whatever, store them as a file in a volume, and then when the app container starts up, well, it just sees a volume in a file. So it's much the same idea as the secrets, in which I'm creating this volume that has files in it, but instead of using the Kubernetes native config map and secrets and everything, I use another container to populate it. And so again, what allows my app container to do is the app just simply reads config from a file. Cool. How that file got populated, got put there, could have been a Kubernetes secret volume mounting. It could have been a init container that fetched secrets from Vault. It just opens up the possibilities quite a bit. There are other init containers that may register applications, what are called part of service meshes, which we're not going to talk about in this class, but in larger kind of network environments, you'll see init containers or sidecars do that as well. But again, the idea is the same. I've got some containers, some processes that run before the main app, and they have to exit successfully. Okay. Here's an example of one that kind of goes along the example I was talking about. Now, the images and commands here are just ones that I made up here. These aren't real ones, obviously. But I have an init container that's going to load secrets from Vault. So I specify some environment variables of the address and what role it should authenticate it, what secret it should pull from Vault, and where to store the secret data. In this case, it's going to put it /config /data.json, and /config is a volume. So this container would start up, would run, would exit, hopefully successfully. And then once it does so, then the main container can start up and it can pull the data from the same volume that's mounted into this app. And this app knows to read its config from /config /data.json, for example. Okay. And the volume here, now this is a new type of volume that we haven't talked about before. It's called empty dir, which basically just means it's an empty directory. Okay, so there's no secret, there's no config map. It's just kind of going back to our USB stick analogy. It's just an empty USB stick, and things I put into it, everybody else that has this volume out can access and use it. Okay, so that's a pretty simple example, but it's a pretty commonly seen one as well. Sidecar containers are useful in a variety of scenarios. Proxy requests in and out of the main app. In fact, here in just the last couple of weeks, I've been working with the IT security office here to deploy some applications on our platform clusters. And they're doing actually exactly this, where they have the main app container, which doesn't have authentication built into it. It doesn't know how to use the Virginia Tech login and all that kind of stuff. But what they're doing is they're using a sidecar container that's running Apache with some CAS modules and whatnot. And so when you access the app, you're actually hitting the sidecar. It does all the authentication and everything. And if you're authenticated and in the right, authorization groups, that kind of stuff, if all that works, then it proxies the request and sends it to the actual app container. And then the app does its thing from there. So it allows, in their case, they're kind of bolting on authentication as a sidecar and proxying the request to the main app. And that's another pretty commonly seen thing. Other proxying may be, we may want to monitor all the network requests that the app is making. And so there are ways to kind of write networking rules so that all the requests go through this sidecar. And then the sidecar can kind of examine and see what am I talking to and how long are the requests taking. So it can do some monitoring. It can also do things like MTLS, which is mutual TLS. And so that's end-to-end encryption between containers or what. So there's a lot of really sophisticated and cool stuff that you can do, most of which is going to be on the scope of this class. But other examples are going to be updating loading configuration, which I'll do an example of here in just a second. And other ones may be, there's lots of log agents that can read logs if the application is just writing the console out, which is what you see when you do kubectl logs. But there are a lot of apps that also write logs to files in the file system. So if the app container is writing into a shared volume that the sidecar container can see, well, then the sidecar thing can say, well, cool, I'm going to take all those log files and ship them off somewhere else to a centralized logging system or something of that sort. So again, the whole idea here is that the containers run side by side. It wasn't a sequential ordering. They run concurrently at the same time. And I'm pretty sure, anyways, we can test this out. If one container exits, it'll cause the whole pod to restart. Okay, so let's actually jump into a demo here. In this case, I've switched back to my local Docker desktop. I'm not running on the Pi cluster anymore. And let's look at our sidecar example that we're going to do here. So in this case, I'm defining a deployment that has two containers in it. Okay, so one container is named app, which is just going to run Nginx, and we're mounting in a volume at user share Nginx HTML cert. Okay, and you may be wondering, why am I doing that? That's a good question. So I've recently been working on a little a tool that can do some encryption in the browser interface. But in order to do that, the JavaScript needs to have the public key that it should encrypt all the data with. And so a way to do that is to, well, make that certificate available to the application. And the public key is available somewhere else. And I don't want to have to, build it into the container image. It'd be nice if it's just constantly kind of refreshing in the background and getting the updated cert. So that's exactly what this is doing. So the app here is just serving contents. And then this other container here that I'm calling the cert fetcher uses a curl image. And the command that it does is basically this while loop that says, I'm going to curl this endpoint, getting the public key, and I'm going to save it to /config/cert.pem. Well, /config, as I see here, is a volume mount that's also mounted into the app itself. And once I do the curl, I wait 10 seconds and try again. So every 10 seconds, it's going to go fetch this public key and then store it in the volume that's shared with the main app. So again, what this allows me to do is my main app code base is just Nginx serving data. I don't have to bundle in any tooling into that container image that's just Nginx to know how to go fetch the contents or to refresh it every so often. I'm kind of bolting on this sidecar that knows how to do it and is constantly just doing it in the background. And then finally, just the volume, and it's an empty dir. Okay, so let's go ahead and apply this. All right, oops, I had it running earlier and didn't undo it. That's okay. So if I ask for my pods now, I see my sidecar demo as well as a couple hello demos that I was doing earlier, but that's okay. Now, if I look at the logs, what it's going to tell me is, hey, you've got multiple containers here. Which logs, the logs from which container? Now, this is something new because normally we're only running single container pods and we don't have to specify this. So in order to get around this, I have to add -c for container and then tell it which container. And this is why the name field in the container spec. Okay, let me go. Okay, So the name and the containers, this is where that comes into play. Okay, so if I wanted to look at the app, there I go. All right. And if I want to look at the cert fetcher, I'll probably see lots of curls going on because it's been running for a little while. All right, now if I port forward 8080, okay. So again, remember everything is sharing the same namespace, and within that, yes, there are two containers running, but Nginx is the one that's listening to port 80. Now, if I curl localhost 8080 cert.pem, I'll get this certificate. Pretty cool. And just to prove that it's the same, if I curl the same thing, okay, let's just pick out, okay, so the last full line starts with 7C, I don't know if it's 7COBW. Oops. Gotta drop the O flag there. Okay, so 7COBW. So again, this deployment has the sidecar container that's going out fetching it and then taking the file, putting that little USB drive, that volume that's also attached to my main app. And in case you forgot, user share Nginx HTML is the web root. So that's why I did a curl cert/cert.pm. Okay, and that's where it was located in the volume. So again, pretty simple example there. But sidecars are pretty awesome. And so the hands-on for this week is we're going to do just a little bit of experiment with pod scheduling. It's a little hard to do this because most of you don't have access to a multi-node cluster that you can do it with. So we'll just do some basic examples on our local machines, and then finally we'll do some experimentation with different multi-pod deployments, kind of similar to what I just did here, but you'll actually get to try it yourself. So now there are more things that come along with advanced pod configuration that we'll just talk about another time. For example, like network policies and whatnot. So there's still more to cover. There's a lot of things to configure and schedule with pods or configure with pods. And honestly, that's part of the power of Kubernetes, but also a lot of the kind of pain points and struggles because there are so many knobs that can be turned. It's super flexible, but at the same time, it is a lot to learn, and it can be hard to keep up. So keep hanging in there. If you've got questions, feel free to reach out to me. Otherwise, I'll chat with you later, and have a good one. Thanks.